This introductory slide presents the topic remote sensing for urban resilience, planning tools and practices, and makes clear that the focus now shifts from conceptual foundations to practical implementation. The session explains how planners and analysts move from raw satellite or UAV images, through a series of processing steps in specific software environments, to maps and indicators that can be used in real decision-making. It highlights that, in the context of EPD-Net, this topic serves as a bridge between earlier lectures on basic remote sensing concepts and later, more hands-on exercises or case studies. The slide briefly signals that the presentation will cover commonly used datasets, key software tools, standard processing workflows, and examples of how these are combined in planning projects aimed at heat risk reduction, flood management, or green infrastructure design. Here we outline the structure of the session to give students a clear roadmap. The first part introduces core remote sensing datasets that are widely used in urban resilience work, ranging from open missions such as Landsat and Sentinel to UAV imagery. The second part presents the main categories of tools: desktop GIS platforms, specialized remote sensing packages, and cloud computing environments. The third part describes typical workflows that transform imagery into planning-relevant products, including pre-processing, index calculation, classification, change detection, and integration with other spatial data. The final parts of the session illustrate these workflows through concrete urban resilience applications and conclude with a short list of good practices and key messages. By previewing this structure, we help students understand how individual details fit into a coherent picture. The learning objectives clarifies what competences students should acquire. After this topic, they should be able to choose appropriate remote sensing datasets for typical urban resilience questions, such as mapping heat islands, flood-prone areas, or green infrastructure. They should be familiar with the main software environments in which these datasets are processed, including desktop GIS, dedicated remote sensing tools, and cloud-based platforms, and understand the advantages and limitations of each. Students are expected to describe, at least in broad terms, the sequence of steps that convert raw imagery into analysis-ready products and then into planning indicators, including pre-processing, computation of indices, classification, change detection, and accuracy assessment. Finally, they should be capable of explaining how the resulting maps and statistics are used to support spatial planning, infrastructure design, and policy decisions in the context of urban resilience and ecological design. Here we introduce the satellite missions that form the backbone of many urban resilience analyses. The Landsat series is highlighted for its multi-decadal archive at 30 meters spatial resolution, which is extremely valuable for detecting long-term urban expansion, loss of green space, and trends in land surface temperature. Sentinel-2 is described as a multispectral mission with 10 to 20 meters resolution and short revisit times, making it well-suited for more detailed mapping of land cover, vegetation, and surface characteristics within and around cities. Sentinel-1 synthetic aperture radar data provide all-weather imaging, offering critical information during cloudy or rainy conditions and enabling applications such as flood mapping or monitoring of ground deformation. We also briefly mention coarser sensors such as MODIS or ASTER, which are useful for regional climate indicators, and commercial very high-resolution missions that provide meter-level detail for detailed exposure analysis where budgets permit. Understanding these options helps students select appropriate datasets for different planning tasks. We explain the role of UAV and airborne data in urban resilience projects. Unmanned aerial vehicles equipped with RGB, multispectral, or thermal cameras provide very high spatial resolution, often at centimeter scale, allowing detailed observations of individual trees, roofs, small channels, or damaged structures that are invisible in satellite imagery. In some regions, governmental or research institutions also operate aircraft carrying cameras or lidar, producing orthophotos and 3D point clouds that capture building heights and detailed terrain. We stress that such data are particularly useful for neighborhood-scale analyses, monitoring pilot nature-based solutions, carrying out post-disaster damage assessments, or validating classification accuracy of satellite-derived products. However, UAV and aerial surveys require careful planning, permissions, and data management. Rather than replacing satellites, they complement them by providing detailed snapshots for selected areas that can be linked back to city-wide patterns mapped from space. We highlight desktop GIS platforms, such as QGIS and ArcGIS, as the main workbenches where remote sensing outputs are combined with other spatial data for planning. We explain that GIS software allows users to visualize satellite imagery, derived rasters, and vector layers, such as roads, parcels, or administrative boundaries, in a common coordinate reference system. Basic processing functions include clipping images to the study area, reprojecting datasets, performing raster arithmetic, for example to compute indices, and joining attribute tables. Crucially, GIS is where remote sensing layers are overlaid with socio-economic data, infrastructure networks and zoning information to produce interpretable maps and statistics. Here we also note that GIS offers cartographic tools for designing map layouts, legends and annotations suitable for reports, workshops or policy documents, making it a key interface between technical analysis and planning practice. Here we focus on specialized remote sensing software and plug-ins that extend the capabilities of general GIS. It notes that the Snap toolbox is widely used for processing Sentinel data, offering modules for atmospheric correction, radiometric calibration, mosaicing and band mathematics. Within QGIS, the semi-automatic classification plugin and other add-ons simplify tasks such as downloading imagery, performing atmospheric correction, computing indices and running supervised or unsupervised classifications. Commercial packages like ENVI or ERDAS, as well as open-source tools like Orfeo Toolbox, provide additional advanced functionality, particularly for large-scale or complex classification and change detection workflows. We emphasize that in many projects, analysts move back and forth between these tools, performing spectral processing or classification in a remote sensing package and then exporting the results to a GIS for integration with other layers and for communication with planners. We introduce cloud-based platforms and data cubes, which have become essential for handling large volumes of remote sensing data. It explains that platforms such as Google Earth Engine, ESA's DIAS services or national data cubes host petabytes of satellite imagery and provide server-side processing capabilities, enabling users to analyze decades of data without downloading them locally. Users write scripts in web-based code editors to perform operations such as filtering images, masking clouds, computing indices, compositing seasonal mosaics or running classifications, and then export summary layers or statistics. For urban resilience applications, such platforms are especially valuable when analyzing long-time series, comparing multiple cities or screening large regions to identify hotspots of heat, flood risk or land cover change. We note that while cloud platforms reduce hardware constraints, they require a certain level of programming literacy and careful documentation of code and parameters, particularly when outputs are intended to inform high-stakes policy decisions. We outline pre-processing, the first step in any robust remote sensing workflow. We explains that analysts begin by selecting appropriate images based on acquisition date, season, cloud cover percentage and sensor type, matching the timing to the phenomenon of interest, for example, peak summer for heat island analysis or wet season events for floods. Geometric correction and co-registration ensure that multiple images and auxiliary datasets align spatially, which is essential for change detection and overlay analysis. Radiometric and atmospheric corrections convert raw digital numbers into surface reflectance or temperature values that are comparable across dates and sensors. In many applications, images are mosaic to cover large metropolitan regions and clipped to the specific study area boundaries. We note that careful pre-processing reduces artifacts, improves comparability and provides a trustworthy basis for later steps such as index calculation, classification or time series analysis. We describe the use of spectral indices as simple yet powerful tools for extracting thematic information from multispectral imagery. We explain that vegetation indices such as NV and EV combine red and near-infrared bands to quantify vegetation greenness, which can be related to ecosystem services like cooling, shading and storm water retention. Built-up indices such as the Normalized Difference Built-up Index, NDBI, highlight impervious surfaces and help delineate densely urbanized areas that may be prone to heat stress or flooding. Water-related indices such as NDWI or its variants enhance water bodies in wet areas, supporting analyses of drainage networks, flood pathways or water scarcity. We underline that these indices are often the first step in many workflows. They can be used directly as continuous indicators, or they can feed into classification and segmentation algorithms that produce discrete land cover maps. We explain how classification techniques convert continuous spectral information into categorical land cover or land use maps. We introduce the distinction between unsupervised methods, which automatically group pixels based on spectral similarity without prior labels, and supervised methods, which rely on training samples representing known classes such as built-up, vegetation, water or bare soil. Training data may come from field surveys, existing maps, high-resolution imagery, or expert interpretation. Once a classifier is trained, it is applied to the entire image to assign each pixel to a class, producing maps that can be used directly to estimate areas of different land cover types, evaluate the balance between gray and green infrastructure, or support zoning decisions. We emphasize that classification accuracy depends strongly on the quality of training data, the choice of algorithm, and the appropriateness of classes for the planning question at hand. We focus on methods for assessing change over time, which are central to resilience planning. We explain that simple before and after comparisons of indices or classifications can reveal where urban expansion has occurred, where vegetation has been lost or gained, and where surface temperature has increased. More formal approaches involve computing land cover change matrices that quantify transitions between classes over specified periods. Time series analysis using multiple dates, sometimes dozens or hundreds of images, can uncover long-term trends and seasonal patterns in variables such as vegetation greenness or land surface temperature. We note that such analyses support questions about urban sprawl, loss of wetlands or agricultural land, and the effectiveness of interventions such as new parks, restoration projects, or flood protection measures. By linking past trajectories to current conditions, change detection results help planners anticipate future vulnerabilities and design adaptive strategies. Here we emphasize the importance of validating remote sensing products before they are used in planning. It explains that accuracy assessment typically involves comparing classification results or derived indicators with independent reference data obtained from field surveys, high-resolution imagery, or trusted maps. For categorical maps, confusion matrices summarize how often each class is correctly or incorrectly assigned, and metrics such as overall accuracy, users' accuracy, producers' accuracy, and kappa coefficient are computed. For continuous variables, correlation coefficients or error statistics may be used. We stress that documenting accuracy and uncertainty is not merely a technical detail, it directly affects how much confidence planners and stakeholders can place in the resulting maps. Transparent reporting of validation methods and limitations helps avoid overinterpretation of products and supports informed, cautious use in decision-making. We show how remote sensing outputs enter the broader GIS-based planning workflow. We explain that indices, classifications, and change detection results are imported into GIS and overlaid with demographic layers, infrastructure networks, and administrative boundaries. Through multi-criteria analysis, these layers can be combined, often using weighted sums or decision rules, to produce composite indicators such as heat vulnerability indices or flood risk maps. Zoning maps can then be derived to delineate high, medium, and low-risk areas, or to identify priority zones for interventions like tree planting, drainage improvements, or new public spaces. We emphasize that this integration step is where technical products are translated into planning-relevant information, and that choices about indicators, weights, and thresholds should ideally be made in dialogue with planners, stakeholders, and local communities. Here we address the communication of remote sensing results, which is crucial for impact in planning practice. We explain that well-designed static maps, with readable legends, consistent color schemes, and clear annotations, remain indispensable for printed reports, planning documents, and public presentations. At the same time, web maps and dashboards, built with tools such as ArcGIS Online, QGIS Web, or custom applications, allow interactive exploration of layers and indicators by planners, decision-makers, and community groups. We stress that visualization must be accompanied by short, accessible explanations of data sources, processing steps, and key uncertainties so that users do not misinterpret the maps. Effective communication turns technical outputs into shared knowledge resources that can support dialogue, negotiation, and collective decision-making around urban resilience. We summarize a set of good practices that increase the reliability and usefulness of remote sensing workflows in planning. We emphasizes that every analysis should begin with a clearly articulated planning question, such as, where are the hottest neighborhoods, or, which areas combine high flood hazard and vulnerable populations, because this guides the choice of datasets, resolutions, and methods. Data and methods should be matched to the spatial and temporal scale of the problem and to available resources, avoiding overcomplicated approaches when simpler ones suffice. We highlight the importance of documenting data sources, pre-processing steps, algorithms, parameter settings, and validation procedures so that results are transparent and reproducible. We also remind students that remote sensing should be complemented with local knowledge, field observations, and stakeholder input Together, these elements create a more complete and socially grounded understanding of urban resilience challenges. In this slide, we provide a concrete example of a workflow for mapping urban heat risk. It describes how analysts can select cloud-free summer imagery from Landsat for thermal bands and Sentinel-2 for high-resolution multispectral data, perform pre-processing and calculate land surface temperature in NDVI. The NDVI layer reveals the distribution of green spaces, while land surface temperature indicates hot spots. These layers are then brought into GIS and combined with population density and building density data to create a composite heat risk index, for instance through normalization and weighted summation. The resulting map highlights neighborhoods where high temperatures coincide with dense populations and limited vegetation, which can be interpreted as priority areas for tree planting, park creation or other cooling measures. We illustrate how each step, dataset selection, index calculation, integration and mapping, is tied to specific planning decisions. In this slide we offer a second worked example, this time focusing on a screening-level flood exposure assessment. It explains how a digital elevation model is used together with river network data and land cover maps to delineate low-lying flood-prone areas and to understand surface runoff patterns. Where available, SAR-derived flood extent layers from past events can be added to calibrate or validate these susceptibility zones. In GIS, these hazard layers are overlaid with building footprints, road networks and locations of critical facilities such as hospitals, schools or power stations. The resulting maps identify areas where high hazard coincides with dense infrastructure and population, indicating zones of elevated exposure that warrant more detailed modeling or field investigation. This example demonstrates how remote sensing-derived information is often used at an early stage to prioritize where scarce resources for detailed studies and mitigation measures should be directed. Here we reiterate the core ideas of the topic. We emphasize that remote sensing provides a wide array of datasets, from global satellite archives to local UAV surveys, that can be transformed into meaningful information for urban resilience planning when appropriate tools and workflows are used. Students are reminded that practical work takes place in a combination of desktop GIS, specialized remote sensing software and cloud platforms, each serving different roles in the processing chain. Standard workflows generally start with pre-processing, move through index calculation and classification or change detection, and culminate in integration with other spatial data in GIS. The slide stresses that beyond technical skills, good practices in documentation, validation and communication are crucial to ensure that remote sensing-based products are credible, understandable and genuinely useful for planners, designers and stakeholders engaged in building more resilient cities.